All right, good morning to Calc 2 people. So we were talking about partial derivatives last time, so we're going to keep going with that. And bring up my little thing here. I've got my handy dandy calculus book here to kind of go through and deal with some things. So I guess we could start off with a partial derivative example to finish what we were doing yesterday. Okay. Actually, this is not partial derivatives. This is something else. This is partial derivatives with no maximum minimums. So let's go through. Actually, let me do this. We are going to resume. Okay, let's look at this one. This is 1 minus the cube root of x squared plus y squared. Okay, that's my f. Okay. One of the biggest problems I've seen is that you guys have a little bit of trouble like dealing with outside function, inside function stuff. Okay, so if I'm going to take this derivative with respect to x, okay, we're going to hold the y constant for this step. Okay, let's rewrite this. This is 1 minus x squared plus y squared to the 1/3. Our first job here is to take the derivative of the cube root function. So that's going to be, well, the derivative of 1 is 0. So we're going to say this is negative, and we have 1/3. Leave this alone for now to the negative 2/3, right? That's the cube root function derivative. Now we've got to apply chain rule because we have stuff inside of this that we also have to take the derivative of. And since we're holding y constant, the derivative is going to be of this 2x piece here. So our value is going to be negative 2/3 x squared plus y squared to the negative 2/3. Okay. When I want to take the derivative with respect to y, okay, it's pretty much the same idea here. Okay. So there's an x here. Missed that. Okay, if I wanted to write this a little bit nicer, negative 2/3 x over x squared plus y squared to the 2/3. Okay. If I take the derivative with respect to y, we're going to get pretty much the same thing because it's a rather symmetric formula, rather symmetric function. So we're going to have negative, again, dealing with the cube root function. The 1/3 comes down in front. We have an x squared plus a y squared, and then negative 2/3 for the cube root function. And then we need a chain that's going to be times a2y. Okay, x in this case is constant, so 2y. But we don't get rid of the x here because it's still inside. We're still taking the derivative of the cube root function first. Okay, so what we're going to have is negative 2/3 y x squared plus y squared over negative 2/3. Okay. Now, if I want to take the derivative of x again, okay, so we're going to get d squared f dx squared, or f xx. Okay, so this is what I got to deal with. Now, it's your choice. There's a lot of things you can do here. You could do some kind of a product rule because we can keep this as a negative exponent. Okay, because we're going to have a product rule with a chain rule. Or we could do a quotient rule, okay, which we're still going to be stuck doing a chain rule. So I would say, you know, I'm happier with the product rule than I am with the quotient rule because I don't have to memorize like which one comes first because there's a negative sign in there and I could mess up. So I'm partial to I'm likely to want to do the product rule rather than the chain rule, okay, or the product quotient rule rather. Sorry. So what we're going to do is we're going to plug this in and we're going to say, well, first we're just going to take the derivative. We're going to say negative 2/3 x squared plus y squared to the negative 2/3. We have this thing times that thing. That's why we need the product rule, right? We have one function over here and one function over here. We can't just push this in because I got a cube root, okay, or a square root. You can't just push this stuff in like that, okay? It doesn't work, okay? For the people who are doing this, x plus y squared, you can't distribute the exponent, okay? This is not like this, okay? That will make you incredibly sad and me incredibly angry, okay? I will not be happy if you have to do that. So, well, I mean, not that angry, but I mean, I will be disappointed, okay? So be careful about the exponents. There's a couple of things you should have learned in intermediate algebra. When in doubt, FOIL, okay? So you should, if you want to do something like this, you got to FOIL it. But there is no like x plus y. Like there's nothing. Well, there's a couple of approximations you could make, but we don't really show you guys that just yet. But that's it. That's what we're doing with it. Okay. So don't. There's nothing you could do just to simplify this. Okay. There's things you can do to approximate it, but there's nothing you can do to simplify it. Okay. You're just stuck. So don't distribute powers. Just try to make sure you're not doing that. So if I want to set this up, this is going to be negative 2/3 x tick, the derivative of the first, times the second, plus the first. Let's get rid of this thing here. Okay, times the derivative of the second. Okay, and I'm not taking derivatives just yet. I'm just kind of leaving a trail of breadcrumbs so that I can see what I've done, because there's a lot of different moving parts to this, and you don't want to do too many parts at one time because you start losing what's going on, and that's when I make mistakes. So let's go ahead and do that. So this derivative, negative 2/3, because derivative of x is going to be 1, and then times the second. Okay, plus, and then we just have a negative 2/3 x. Okay, and now we have to take this derivative. Well, what's the derivative of the negative 2/3 function? It's negative 2/3 times some stuff to the negative minus 1. That's 3/3. So minus 2/3 minus 3/3 is minus 5/3. Okay, x squared plus y squared. We leave that alone because it's inside of the outside function, right? Just the outside function first. Then times, we need the chain rule, okay? And that's where you're going to have the derivative of the inside, and that's going to be where your 2x turns into. And then derivative of y squared is just 0 because y is constant. Okay, now we got to put this together. Okay, so we've got negative 2/3 x squared plus y squared to the negative 2/3 minus, got to get rid of all of this stuff. Well, the 2/3 and the 2/3, they can all combine. Those are just constants. So this is 2, 4, 8. 2 times 2 times 2 is 8. We've got 3 times 3, that's 9. Okay. We have, how many negatives do we have here? We have 2 negatives. So it's going to be a 1, 2, 1, 2 negatives. So that'll be a positive there. All right, how many x's do we have? We have 2 x's. Okay, and then we have x squared plus y squared to the negative 5/3. And you say, well, let's take another derivative. Let's not. Okay, this doesn't look like it's going to get any easier as we go forward. Okay, but that's how you would find the second derivative. This would be f squared dx squared. Okay, so just be careful of that. All right, I'm sorry I took us down the tangent here. Calculus joke. But there we are. Okay, I would not put a problem like this on a final for you to like figure out where this is going to be equal to 0. Okay, that's just not a very polite thing to do to you. Okay, we're still going to have x squareds and y squareds. It's going to be a mess. So this would be a poor problem to pick. All right, I picked the ones that are kind of like in your book. So there we go. Okay, but just to give you a little bit of review for this. All right, let me pause and I'll give you a double integral one. Okay, because we haven't done one of those yet. Okay, let's try this one. Okay, again, I picked these out of your book. I did not pick them out of a random book, so that I'd be sure that you will have seen at least problems of that type before. So some of the regular calculus books, I mean, we'd certainly not give you like stuff with trig in it because you've never seen it, right? But some of them are a little bit, it may have different integration techniques required than the ones you've seen before. Okay. So let's go with this one. We have an integral. Okay, just put an R down here. We'll get to that in a minute. I've got an xy cubed over an x squared plus 1. We have a dA. Okay, and then they tell us that R is from 0 to x to 1. And we have 0 to y to 2. Okay, so this is an integrated integral. You can do them whichever order you please. Again, sometimes some orders are better than others, but for the most part, like this is up to you as to decide, what do I want to do, x first or do I want to do y first? Okay, let's deal with the x first. Okay, so our integral is going to be, okay, 0 to 1, 0 to 2. We have x squared plus 1, and we have a y cubed here. Okay, dx, dr, or dy rather. Notice that what we're going to integrate here, we don't have a plus in here. This is y, this is x times y cubed. We can move this y cubed out before the x integral only. Okay, don't take it all the way to the end. This just goes to the x one because as far as x is concerned, this y is a constant. And since it's times, we can move it out. It'd be like having an 8 here, right? 2 cubed would be 8. We can just move it out before the, before the x part of the integral. Okay, not all the way out. You can't move variables all the way out of the integral. Okay, but you can move variables which are considered constants through the integral side. Okay, so we're going to have 0 to 2 y cubed. Okay, and then we're going to have 0 to 1 x over x squared plus 1. Okay, dx dy. This isn't too bad, right? Because we can set u is equal to x squared plus 1. Du would be 2x. Okay, and we have a 2x to deal with. Well, we don't have 2, but we can fix that. Okay, so we're going to have 0 to 2 y cubed, 0 to 1. And here I have my x. I set this to be u. Okay, and what I'm going to do is I'm going to put a 2 and a 2 here. So now look at that. I got a du. This I'm just going to move that to the end because again, the integral doesn't care about the 2. Let's move that through. So this is going to be 0 to 2. I'm just going to put it here so I can keep it with my y so I don't end up losing track of it by putting it way up here and I have to remember it. Okay, it's like, you know, where Pluto is for the solar system, people will forget. So here we have, okay, 1 over u, right? This is 1/2 that I didn't include. And then du, that 2x is the du, 2x dx, okay? So what's the integral of 1 over u? Well, that's one we should know. That's 0 to 2. We have ln, oh wait, don't get carried away here. Okay, we have 1 over 2, or 1 to 2 of 1/2 y cubed, right, times this integral. This is going to be natural log of u. Okay, and we're going to go from 0 to 1. What the heck was u? This was ln of x squared plus 1. Okay, I was a little concerned about seeing that 0 here because I was a little worried about it. But this is always going to be a positive number. Okay, we don't have to worry about the absolute values because this is always positive. We're going from 0 to 1. Okay, do you remember what parabola, right? X squared plus 1. So I'm going to look at x squared plus 1. That was a parabola that was has a vertical shift of 1. We just move the parabola above the axis. All of these numbers are positive. Okay, that's why we can say that. Okay, so let's go ahead and put this in. So we have 0 to 2, 1/2 y cubed, and then we have ln of 1 squared, which is 1, plus 1 is ln of 2. Okay, minus ln of 0 squared, 0, 0 plus 1 is 1. What is the natural log of 1? Well, that's 0. So here we have our integral from 0 to 2. Okay, we have ln 2, this was 0, over 2 y cubed. Again, I would just move this through. Okay, I don't want to look at it. It looks a little intimidating. Okay, we just put it there and deal with the 0 to 2 here, y cubed. And now we just have to integrate y cubed. You could do that. It's y to the 4th over 4 from 0 to 2. Okay. I'll group the 4 up with that 2. So 2 times 4 is 8. So we have natural log of 2 all over 8. Okay. And then we have y to the 4th from 0 to 2. Okay. So ln 2 over 8. 2 to the 4th minus 0 to the 4th. 2 to the 4th, inch showing gives me 16. So this is 16 over 8 ln 2. Okay, 16 over 8 is 2 ln 2, and we are done. Okay, so that's how you would integrate that. All right. Let's look at one a little bit harder. I'm going to pause this for a moment so I can see one. All right. The goal for the other integrals that I'm going to give you, the goal is not to find the hardest problem that you can do, the hardest problem that I don't think you can do. The problem is to give you an integral which I think is going to assess you fairly. Okay, so just realize, like, if they're getting to be too much, that is not the integral. That if you're trying to find other problems, it's not the integral for you. And actually, I rather like this book for their partial integrals or their double integrals, because they always come up with physics integrals. Okay, what do you mean by that? I mean, physicists are amazing. They go through all sorts of substitutions and simplifications to do things like integrate. Usually a physics integral is this. Okay, and it is truly amazing to watch them work the problem, get down to something like this, where they're only integrating like a dx. Okay, it might be a d phi or something because of all the substitutions they've made, but it is truly amazing to watch them like sit there and get a sledgehammer out, just keep hitting this function until it gets smaller and smaller and smaller until that's the calculus that they feel comfortable with. It's awesome. So so yeah, don't look at physicists and say, oh, you're dissing physicists here. No, I'm pretty in awe of what they're doing here. Okay, so let's see if we can come up with one that's reasonable. Where was it? I saw you. That was reasonable too. We'll do that one. So we've got a integral of 1 to e. Okay, and then we have a 0 to ln x. All right, and we have an x, y, dy, dx. Okay, so we're going to integrate y first because that's the first dx. And when you have these sorts of problems where you have to deal with this, if you want to change them, you're going to have to graph it. Okay, I don't want to change this. Okay, but if we wanted to integrate y, right, from 0 to ln x, right, we'd be integrating for this. We would also need to go from x going from 1, I'm sorry, 1 to e, right, to here. So we'd have to have this region here, and then we have to convert. Okay, I don't recommend doing it that way. I did not pick a problem where it's like, oh, it would be easier if you did it the other way. No, didn't pick that one. Okay, I just picked it so you can just integrate in order and not have to worry about it. Okay, so the x, we're not going to care about the x just yet. We can move the x through out to here. Okay, we're only integrating with respect to y first. So what we're going to do is we're going to say, well, this is from 1 to e, here's an x, and then we have a 0 to ln x of y dy, and then we have a dx here. Okay. This one also, I don't think I picked this one because this requires like a number of different steps, but the idea of what we're doing is going to be the same. Okay, so integrating y dy, isn't that y squared over 2? Going from 0 to ln x. Okay, here's 1 to e of x. Okay, and then we have our dx still. Probably would have been better to go in the other direction because it get e's a little bit easier to deal with. But we didn't. Okay, so here we go. It's this integral from 1 to e of x over 2. Okay, and then what are we going to have here? We're going to have ln x squared minus 0 squared. Okay, oh, this is delightful. So here we go. We have 1/2 integral 1 to e of x ln x squared. Okay, dx. The 0, no matter what we multiply against it, is still going to be 0, so we'll be set there. Okay. Now, we talked. This is a bad problem for this particular problem, but it's a good problem overall because what do you know about a polynomial and a logarithm? And you know you need integration by parts here, don't you? Okay. So let's go ahead and we'll set u equal to ln x squared. Okay. And we'll say our du is going to be 2 ln x times 1 over x, right? Because we're still going to do a chain rule here. And our dv, that'll be x dx. Okay, and our v is going to be x squared over 2. Okay, so remember our integration by parts formula, we do this, right? Diagonal times the cross there on the bottom. So we're going to have this is 1/2. Okay, uv, so that's going to be x squared over 2 times ln x squared. Okay, minus integral, right? This is going to, I'll just write out the whole thing. So this is 2 ln x times 1 over x times x squared over 2. Clearly, we could make some stuff go away here, right? We could do some stuff here. So the 2's are going to cancel, and we have x squared over x, so that's just going to be x. So this is going to be 1/2 big parentheses, and we're going to have x squared over 2 ln x squared minus integral. 2's cancel, so one of the x's cancels. We have x ln x. Okay, what joy. We got to do it again. Let u equal ln x. Du equals 1 over x. dv equals x dx. And v is equal to x squared over 2. Okay. So again, applying our integration by parts here, we have that. So we have 1/2 x squared over 2 ln x squared minus, okay, and then we have integration by parts. So it's going to be minus, okay, that's going to be 1/2 x squared ln x, these two together, minus integral of 1/2 x squared over x is just going to be x, isn't it? Okay. So, and this is going from 1 to e. Actually, it's going from 1 to e here too. But so let's see here. We have 1/2 x squared over 2 ln x squared. Okay, minus we have 1/2 x squared ln x minus. We have to integrate 1/2 x. You could do this. We can all do this. Right? It's just that. Right? And we're going from 1 to e. Okay. So cleaning this up a little bit, we have 1/2 out here. I'm going to get to that in a minute. X squared over 2 ln x squared minus 1/2 x squared ln x. Okay. Yeah, we're okay. Okay. And then minus times a minus is a plus. Okay. And we're going to have our x squared over 4 from 1 to e. Okay. Now, if you want, you can factor this in. Okay, so it's going to be x squared over 4 ln x squared minus 1 over 4 x squared ln x, okay, plus x squared over 4. Oh no, 2 times 4 would be 8. Okay, and now we're going to have 1 to e. Let's plug in e. So we have e squared over 4. What is ln of e? ln of e is 1. 1 squared is 1. So this is just e squared over 4 minus 1/4 x squared, oh no, sorry, e squared times ln of e. ln of e is 1. So here we have 1/4 e squared. Okay. And then last but not least, we have a e squared over 8. So this is going to be plus e squared over 8. Hey, look at that. You have an e squared over 4 minus an e squared over 4. That's 0. So we'll just have e squared over 8. Right? If I plug in 1, here's what happens. Right? Do you know what the natural log of 1 is? Okay, test that out. That's 0. Okay, so this term is 0, this term is 0, and we just have minus 1 over 8, right? So it's minus. Okay, so we end up with e squared minus 1 all over 8. Okay, or e plus 1 over 8. E plus 1 times e minus 1. I guess we could do that for difference of squares. But now this is your answer. Okay, and that's how you do this. Okay. So let's see here. We have double integral. Okay, we did both a standard one. We just had numbers, which means you could do them how you please. And then we had when the bottom is like a weird shape. Okay, the limits tell you like what region you're integrating over. Okay, so when we did that, I guess where we did it down here, we're integrating over this like weird kind of cusp thing. Okay, that's the shape we're integrating over. So if you shine the flashlight straight down on what we were integrating, this is the shadow it would make on the ground. Okay, so there's our problem. Okay, so let's see here. We did that. Hold on for a moment. All right, there she is. She's making too much noise. Okay, she is adorable though, so we'll tolerate it. Okay, there you go. She's a good girl. I know, she just wants a boyfriend. Okay, so she doesn't like being held though, so I'm gonna put her down. Off you go. All right, back to sharing. Back to calculus now. Okay, so she is very cute. All right, so let's see here. We were going to talk a little bit about, we have double integrals. We did that. L'Hopital's rule. Remember L'Hopital's rule? Okay. Okay. So the issue here, right, is you need an indeterminate form. All right, so you need a 0 over 0, or you need an infinity over infinity. Neither of these are automatically 1. Okay, this is not 1. No. Okay, equals 1. No. Okay, you have to apply the limit in order for this to work. Okay, so if you get an indeterminate form, your answer isn't, oh, it's 1, I'm done. Like, your answer is, oh, aha, I've got to use L'Hopital's rule in order to investigate the rest of this. Every time you use L'Hopital's rule, you have to reevaluate your limit and see what happens, because sometimes you have to use this more than once. Okay, so let me go ahead and stop this from, I'm sorry, another intermission here. All right, so again, I used your book for inspiration, but this book has ones that are a little bit harder for you guys. You got to be judicious about what you're asking. Okay, so what do we have here? We have, saw one that was really good. I was like, oh, I wish I had waited. Wish I had looked at this book before I started writing your test. Okay. But maybe not. Maybe not. This is, where are you? I want ln of x squared 2x. There we are, divided by ln x. Okay. And we are looking for the limit as x approaches 0. Okay. Okay, so we want limit as x approaches 0. Okay, of natural log x squared plus 2x all over natural log of x. They're kind of nice. They give the problem to us at a fraction anyway. We don't have to do any operations to make it a fraction. If I plug in 0, top and bottom, limit where x is going to 0 from the top here, that is, right, what's the natural log look like? Looks something like that, regardless of what's in there. So it's going to be negative infinity over infinity. So those cancel. And look at that, we get an indeterminate form. Hooray. Okay. So now that we know we have an indeterminate form, we can apply L'Hopital's. I'm going to go ahead and erase my little graph here. All right. So we know apply H. Right. So what are we going to have here? We're going to have that. What's the derivative of the natural log function? It's 1 over, right? So we have 1 over x squared plus 2x times the change. So what is the derivative of this piece here? This is just 2x plus 2. Okay. Now, what's the derivative of the bottom? It's 1 over x. Okay. Well, this looks delightful to kind of have to sort through. Okay, so we have 2x plus 2 over x squared plus 2x divided by 1 over x. Okay, so that's effectively, right, 2x plus 2 over, I'm going to go with, let's say, x plus 2, because I have a feeling I know what's going to happen here, divided by 1 over x. That's what we're doing. Okay, so we're going to say this is 2x plus 2 over x plus 2. Do you remember what you do when you divide a fraction? Okay, and multiply. Those cancel, thankfully. So we end up with 2x plus 2 over x plus 2. And if I plug in for, right, what do I do if I plug in? I got to plug in for 0. Do we get a value? Well, we get 2 times 0 plus 2 over 0 plus 2. So in this case, it is 2 over 2, which is 1. So in this case, it did work out. But you have to go through and do this. Okay, if you just tell me this, it's not quite right. Okay, so my favorite example, right? 16 divided by 64. Okay, plug that in your calculator, see what you get. 1/4. Would you have, if you had a kid, if you had a child, and they came home and said, "Look, Mom, Dad, I learned how to divide. I learned how to deal with fractions today." You would be a little upset with that teacher. Okay, it's a cool trick. Okay, so 19 divided by 95, cancel the 9s, you get a 5th. Type this into the computer, you will, or type this into your calculator, you really will get 1/5. Okay, do not show this to somebody who is in 3rd or 4th grade. You will screw them up for the fractions for the rest of their lives. Okay, if you ever have anybody who's claims that they're good at math, you can show them this and see how they're dealing with it. But do not show this to a child. But if my kid came home and they said, "Look, I can deal with fractions," I would be beyond upset. Okay, we would be having a meeting with that teacher pretty much immediately. So just because you get the right answer does not mean you got the problem correct. All right, if you end up getting, "Oh, it's 1," and it happens to turn out to 1, that's fine. But if you just decided that infinity over infinity was 1, no, you're going down in flames on that problem. That is not going to work. Okay. Let's see if we can find another one real quick. Again, you have to be careful because a lot of L'Hopital's problems have trigonometric stuff in them. You ain't going to see that. Okay, I'm not even going to put it on there. You also have stuff that you have to do what they call logarithmic differentiation, which means you have to take the log of both sides before you can differentiate it. Okay, and again, I don't believe that was a technique we learned in Calc 1 with you guys, so I'm not going to do that to you, and then we'll see. Okay, so I guess that one kind of works. I think I gave this one to my Calc 1 students last year. Oh, what if they don't give it to you? What if they do something horrible? If they do natural log of no, we don't, not natural log. We do x squared. Right? Is that what I'm looking at? X squared natural log x. Okay, let's do that. X squared line x, and I want the limit as x is going to, where'd you go? As x is going to 0. So, but wait, that isn't a natural log form at all. No, it isn't, but it's a 0 over, it's a 0 times negative infinity. That's not a good form either. Okay, so how do we turn this into a fraction? Well, what we're going to do is we're going to make this a fraction, and then I'm going to multiply by 1 over x squared divided by 1 over x squared. What happens here? Right? We end up with a 1. So we have natural log of x divided by 1 over x squared. Okay. Now we get negative infinity over infinity. Can't do anything with that. We got to apply, right? X equals to 0. X equals to 0 here, we're going to get infinity. Right? X equals to 0 here, we're going to get negative infinity. You say, oh, look, it's a indeterminate form. Use LH. Okay. So we're going to go through and do that. Okay. So what is the derivative of the top? What is the derivative of the bottom? This is L'Hopital's rule. This is not quotient rule. Okay, so be really careful about how you're perceiving this and how you're working the problem. So derivative of natural log is 1 over x. Okay. The derivative of this is equal to x to the negative 2. The derivative of x to the negative 2 is negative 2x to the negative 3. So this is 1 over x divided by negative 2 over x cubed. Okay. Back into a fraction. How do we deal with this? We're going to hit x cubed over negative 2, x cubed over negative 2. What happens? Right, we get x squared over -2. We have limit as x approaches 0. If we plug 0 in here, we just get 0. So we get 0 over -2. We're 0. We're done. Okay, that's what you do. Okay, so just be careful. These could be done multiple times as well. Okay, so be careful about that. But other than that business, that's L'Hopital's rule. Okay, so the steps for L'Hopital's rule: 1, check indeterminate form. Okay, 2, if yes, right? Yes. This not an indeterminate form, you can't use L'Hopital's. But if we have this, then yes. Then we do f prime of x divided by g prime of x. Take the derivative of the top, take the derivative of the problem. 3, reevaluate. 3. Okay, still indeterminate form. Okay, then depending on what your background is, we'll say go to 1. Or I guess we could do it this way. We could say repeat. Okay, but that's what you're going to do until you get something that isn't in an indeterminate form. 2 would be nice. That's not an indeterminate form. Okay, but that's what you're going to do. All right. So I think maybe one more part here. I'm going to go ahead and stop this. Right, and we'll see you in the next one.